All right. And I love the way they're teaching you proofs here. The hardest way to learn proofs is if they don't give you one of the columns. As long as they give you one of the columns, then it's relatively easy to figure out the other column. And here they're giving you one of the columns, okay? Some problems they'll give you the right-hand column for row 1 and then the left-hand column for row 2, but as long as they give you one of the two columns, it's relatively easy to prove it. So what's given here?
3x equals 6 minus 1/2 x.
Okay, hold on a minute. A multiplication property of equality, which basically said that we can multiply both sides of the equation by any number we want. Well, what am I going to multiply both sides of the equation by?
1/2 or 2 over 1?
2, not 1/2. If I multiply this by 1/2, I get 1/4.
Okay.
If I multiply both sides by 2, in other words, I'm going to multiply that side by 2 and this whole side by 2, then I'm using the multiplication property of equality. What does that give me?
6x equals 6 minus x.
You have to multiply the entire right side by 2.
Oh, you do? Okay, then 12 minus 1x.
Right, or just x.
Yeah.
Okay, so now we're there. Now we can look over here and they are looking for the addition property. So what am I going to add to both sides?
1/2 x.
Not 1/2, we're now in step 2.
Oh, just x then.
X. So what's line 3 read? What's the statement should be?
7x equals 12.
And then finally, the last step is the obvious one. In other words, this is the obvious way you would solve this equation. Now I'm going to divide both sides by 7.
Yes.
And that's how you do that proof. Okay?
Okay.
Now, let's go to the next one. Okay. Again, they're giving us all of the reasons. When proofs become hard is when they expect you to do both columns on your own from the start.
Yeah, we have to do that when they do
Proofs are hard. So the fact that they're starting you out like this is really good. It really lets you kind of get your feet wet on how you're supposed to do proofs. Okay. What is the given here?
RT and the line RT and line PQ intersect at S. So RS equals PS and ST equals SQ.
Yeah, I would be tempted not to even write that first part. I don't know that you necessarily need that. You definitely need these two. I think you could probably omit this part. Maybe. You might want to put it in. It can never hurt to put it in. I omitted it for a couple of reasons. First of all, I suppose they do have to intersect. In other words, if those two lines were parallel, then we're going to have a hard time proving what they're asking us to prove. So maybe we need it. I'm still going to leave it out, and you can put it in on your homework if you have to. The second reason is the addition property of algebra. or the addition property of what they call, yeah, I can't even bring that thing back up here, the equality equations, or whatever they call them. So how are we going to use the addition property? What we're trying to prove is this. Where does that go? Got to go down here on line 4, right?
Yeah.
Always the thing you're trying to prove goes on that last line. In other words, if that belonged on line 5, there'd have to be a reason why that's true.
Okay.
Okay? So, the addition property, segment addition postulate. Let's see, we're trying to prove that RT is equal to, in other words, this entire line is equal to that entire line. And what we're given is that RS is equal to PS and QS, or SQ, is equal to ST.
Okay.
So what addition property do we want to do? What should statement 2 read?
RS plus ST
There you go.
equals RT.
Not yet. Let's PS plus SQ. Right? In other words, what I'm doing is adding this equation, that given, to that given. That's all I'm doing. It's the addition property. I can add equations. So I'm adding this equation to this equation, and it gives me line 2.
Okay.
Okay? And it's the addition property of algebraic equalities. Now, the segment addition postulate is the only thing we're missing. Well, what does that say? How do I get from line 2 to line 4? What is RS plus ST?
RT.
Aha. So RS plus ST equals RT, and by the same segment addition postulate, PS plus SQ equals PQ. And now, by the substitution property, I can substitute RT wherever I see RS plus ST. Well, I see it in statement 2. Statement 2 says RS plus ST equals PS plus SQ, and now I'm saying RS plus ST equals RT, so I can substitute RT for RS plus ST. And the same thing with the PQ. And that's my last line, and I get it because of the substitution property.
Okay.
Okay? Is this your homework?
We had homework on it. Our homework's at the end of this. But this is like the other night's homework.
Okay, so this is something you have to turn in?
Well, no, not. It was due the other day.
Okay.
Yeah.
Because we're looking for practice doing proofs.
Yeah.
Okay, well, good. Give me the given.
M, the measure of angle AOC equals the measure of angle BOD.
It's always the easy part, huh? The given.
Yeah.
And last line needs to say what we're trying to prove.
Which is the measure of angle 1 equals the measure of angle 3.
And a lot of times it's helpful to do it this way. Then all you got to do is figure out how you get from 1 to 5 using these reasons over here. Okay. Now, angle addition postulate. If angle AOC what do you think 2 might need to say?
Well, the measure of angle 1 plus the measure of angle 2 equals the measure of angle AOC.
Yeah, perfect. So, and that's why they gave us extra room. Angle 1 plus angle 2 equals, we'll just do it like this for the moment. In other words, I should say M plus M equals M, okay? Like that. And also, along with that, what else?
Measure of angle 2 plus measure of angle 3 equals the measure of angle BOD.
And that's still the angle addition postulate.
Yes.
Now the substitution prop. Well,
the measure of angle 1 plus measure of angle 2 equals measure of angle 2 plus measure of angle 3.
And how do we know that?
Because the measure of angle AOC equals measure of angle BOD.
Okay, so what was your third statement again?
The measure of angle 1 plus measure of angle 2 equals measure of angle 2 plus measure of angle 3.
And that's substitution because we've said statement 2 says that AOC equals 1 plus 2. So all I'm doing is substituting 1 plus 2 for AOC. In other words, I'm kind of doing that in this line. 1 plus 2 is AOC, 2 plus 3 is BOD. They've told us that AOC equals BOD. Therefore, we can get to statement 3 that 1 plus 2 has to equal 2 plus 3. What's statement 4 is going to have to say? And most people would leave this one out. In other words, I would leave this one out. If they didn't give me the reasons here, my fourth reason would be the subtraction property. I would just subtract angle 2 from both sides, ending up with what I'm trying to prove. But what do you have to say with statement 4? Yeah, the reflexive property is the one that says A is equal to A.
Yeah, so what would A be though?
Well, angle 2.
Oh.
In other words, the measurement of angle 2 equals the measurement of angle 2. This is the step that nobody thinks they should have to put in. And I wouldn't either, except they've told us that it's the reflexive property, and that's the one that says A equals A. Okay? And now that I know that measurement of 2 equals the measurement of 2, well, I can subtract equation 4 from equation 3, right?
Yeah.
The subtraction property. And that's what I'm doing. I'm going to subtract angle 2 from the left side of statement 3 and angle 2 from the right side. And what I end up with is the measurement of angle 1 equals the measurement of angle 3.
Okay.
I guess that means the subtraction property of equalities.
Okay.
Let me go up again and, yeah, this is the properties of equalities. And we also have the properties of congruence. And notice that these really aren't any different. Notice the properties of congruence. You still have the reflexive property, which says angle D is congruent to angle D. You have the symmetric property, which says if DE equals FG, then FG equals DE, same as this symmetric property up here. And you have the transitive property, which is the same as this transitive property. So they list these as three separate properties, but they're basically the same as these three, only instead of properties of equality, they're properties of congruence. And let's just briefly talk about the difference between congruence and equality. 5 is equal to 5. But if I have a triangle here, and I say that triangle is equal, well, the only triangle it's equal to is exactly the same. But if I rotate the triangle on the right, I still have, they're not equal anymore, they're called congruent. In other words, those two triangles are congruent, the two at the bottom, but they're not equal. They don't have the same orientation in space. So congruence doesn't mean exactly the same as equal, but for all practical purposes it does.
Okay.
All right, let's go back and let's do some more examples. We did 3. Let's look at 4. Okay. Here they are giving us the left side. And we got to come up with the reasons. This is terrific, actually. Well, kind of bizarre. Hold on a minute. My thing is kind of stuck. All right, that should be enough room. All right, what's reason 1?
Given.
Always. I've never seen a proof that reason 1 was not given. Notice that statement 4 is what we're trying to prove. Ooh. I guess they meant prove that the measurement of angle DEF, right?
Yeah.
That seems to be missing. They just got measurement of angle. They meant measurement of angle DEF.
Okay.
Okay. So now let's see if we can figure out the reason that 2 is true.
Would it just be angle addition property?
It's what?
Angle addition property?
Yes. And they give you quite a bit of leeway here, don't they, on your words? In other words, is that the angle addition property, or is it just the addition property?
I think there's a difference.
Yeah, I think you're right. I think it is the angle addition property.
Yeah, because for a segment, it should be segment.
Okay, cool. And that's what we're doing. In other words, we're adding this equation to this equation. We're adding the two angle equations. Okay, so line 3 says the measurement of 1 plus the measurement of 2 equals the measurements of ABC. What's that reason? Remember the segment property? The segment addition property? So this would have to be the angle segment addition property. In other words, a line is equal to the sum of its segments, and an angle is equal to the sum of its segment angles. So I think that's 3. I might be off on my wording, but I don't think so. In other words, when we looked at example 3, it went through this same sequence of reasons, starting with the addition property and then the segment property and so forth. And this one is the same thing. In other words, this reason 3 applies to all of statement 3.
Okay.
Okay. And finally, what's the reason for 4?
Substitution.
Yep. Okay. Let's go on. Yeah, if we look just back up, notice that we had the angle addition postulate. Okay, we use that in number 4. And we also used, if I go back to 2, the segment addition postulate.
Yes.
Now, is it important that we use the words postulate instead of property of equality?
Yes.
Is it? Okay.
I don't know, actually.
Another reason people hate proofs, because you can understand exactly what's going on, and if you use the word property instead of postulate, you lose points. I'm not sure that that's really true, but we'll try to use the right words.
Okay.
All right, let's look at number 5. Now they're making it a little harder. They're leaving blanks on one of the columns. But number 1 is given. And number 5, what's the statement on number 5 have to be?
SI equals UN.
Yeah. And that's not a bad idea to write in advance. At least I think it's helpful. Okay. Okay, so now we pretty much have the left column. These blanks shouldn't be hard to fill in. What is equal to SI plus IT?
ST.
And what is equal to RU plus UN?
RN.
Based on what?
Segment addition property.
Is it the segment addition property or postulate? I think it's a postulate.
Oh wait.
I'm pretty sure it's a postulate. Here, let's finish the problem and then we'll go back and check. Unfortunately, the way I'm doing this, if I close that out, I don't get to see my writing again. So let's go through the whole problem and then we can kind of go back and have a look and see if that should be property or postulate.
Okay.
Postulate. Okay. Now, SI plus IT equals RU plus UN. Why?
To the substitution.
Yeah, in other words, substituting for that. In other words, number 1 says ST equals RN, and then we say, well, ST is equal to SI plus IT, and RN's equal to this, so I can make this SI plus IT, this right side, equal to that right side. By substitution, again, I'm not sure if it's the property or postulate. We'll call it a postulate, and we'll go back and try to figure out whether that's correct. 4, IT equals RU.
Transitive?
Given.
Let's give it.
Huh? See what I circled?
Yeah.
So that was the given. In fact, we could have written that. I think they're making it a separate statement just to make it absolutely clear. It's not very often you see given in reasons beyond the first reason. But in this case, they didn't put that in statement 1. They could have actually. But it makes actually a little more sense to do it here. And if IT equals RU, how do I get to SI equals UN?
Substitution?
Subtraction.
Oh.
In other words, what I'm doing is subtracting this equation from that equation. The IT's cancel, the RU's cancel, and I'm left with SI equals UN.
Okay.
So that is the subtraction, and I'm pretty sure that is a property of equalities. Now, we got segment addition postulate, substitution postulate, and the subtraction property. Let's see what these things should be called. Well, first of all, if we go back to this, these are properties of equalities. So those are all properties. These are all properties. Where are they getting these postulates from? I don't see anything that says postulate. In the first example, it was all properties. In the second example, it was the segment addition. That is a postulate, I guess. That's not a property. But then it is a substitution property. So far, the only postulate we have is segment addition postulate. And you notice that that was not in that list.
No.
Addition. So they gave that to you elsewhere, I guess. I don't know why they didn't include it in that list, but okay, substitution's a property. Angle addition postulate. Okay, I guess when you're dealing with angles instead of lines, they're postulates, not properties.
Okay.
Again, that's the substitution property, the reflexive property, and the subtraction property. Number 4, I don't know. We put those down, so we can't use that to determine the words. Let's just go on for the moment without definition, a postulate, or a theorem. Look at this. Postulates include the properties from algebra. Well, that's interesting. So I guess I could have put down the substitution postulate as well as the substitution property of equalities. It looks to me like maybe I could have. All right, so what are we doing here? Theorem 2.1 is the midpoint theorem. So if M is the midpoint, then AM is equal to half the total length of the line, and MB is equal to half the total length of the line. That's almost self-evident, but it is a theorem. Now, the one thing in geometry that you don't have to worry about, really, is the numbers on the theorems. There is no standard. You can't go to another school and say, what's theorem 2.7? Their theorem 2.7 is not necessarily going to be the same as your theorem 2.7. So the numbers on these theorems are only for your particular course. So you don't really need to memorize the numbers. When you get to college, this midpoint theorem will be called the midpoint theorem. It will not be called theorem 2-1. Okay? So you need to memorize what the midpoint theorem is and what the angle bisector theorem is. But you don't need to memorize these numbers. At least not for geometry. Possibly for Mullen High School, maybe they will make you memorize those. I'd be amazed if they did. It wouldn't be proper because those numbers are different from school to school. Okay, deductive reasoning is where we are proving a conclusion step by step, stating the reason for each step as given information. Wasn't that what we did on the first 5? Isn't that exactly what we did?
Yeah.
Okay, so we used deductive reasoning on examples 1 through 5, or 1 through 4, whatever we've done.
Okay.
Okay, and then reasons used in proof. Reasons used in proofs. Reasons used in proofs. Given information, that's one of the reasons. So they're listing all of the various reasons that we can use in column 2 of a 2-column proof. Okay, we can say that it was given information. We can say that it's the definition of midpoint, or we can say it's the midpoint theorem, or, and yeah, this is a little tricky. The only way they can teach geometry, and this really is unfortunate, but you can't use a theorem to prove something unless it's already been proved.
What does that mean?
Effectively, it means that if you can't use the Pythagorean theorem yet to prove something. You know what the Pythagorean theorem is?
It's like b squared, or like b equals.
I'll write it down. You'll get this. This is probably the most important theorem in all of geometry. It involves right triangles where that angle is a right angle. That side is A, that side's B, that side is C. In all right angles, A squared plus B squared equals C squared. That is the Pythagoras theorem. Like I said, there's no more important theorem to memorize in geometry. But we haven't gotten there yet. So I don't think they would allow you to use that theorem in one of these problems. You haven't come across it yet. Now, once you're finished with geometry and you've come across all the theorems, and now you go back and you have to prove something, you can use it. And all of these theorems have been proven. That's why I say this is a little bit tricky and has merely to do with the progress that you're using to prove stuff in geometry. They don't want you using advanced stuff to prove stuff that you haven't proved yet, if you can get what I'm saying. I don't know if we'll come across an example so I can explain it a little bit better. That's the best example I can think of. You haven't had the Pythagorean theorem yet, so you wouldn't be able to use that as a theorem for a reason. In other words, if you're looking to do a 2-column proof, I would not be able to say the Pythagorean theorem yet. We haven't proven that yet. At least that's the way most geometry courses work. And that looks like the way this works, otherwise they wouldn't have this in parentheses. You can use theorems as a reason in a proof, but only if it's been proved already, either by you or the book or something else. In other words, this is stating the midpoint theorem, okay? So we can use the midpoint theorem now. And this is stating the angle bisector theorem. So we can do that. We can use that as a reason. Okay, go down and see what we got here. Ooh, they're going to make it tough on us. In other words, they're not giving us any information.
No, except the given.
So what's the given?
M is the midpoint of AB.
You don't have to write the red. Of line AB. And that is given. And let's go ahead and write our last line, even without a number, because I don't know what it's going to be. We'll just leave space. Well, the last line is always what you're trying to prove. AM equals 1/2 AB, and MB equals 1/2 AB. And we don't know the reason yet. We're going to come upon it as we go through this.
Okay.
Now, if M is the midpoint of AB, then what is true?
AM equals MB.
And what's the reason why that is true?
Definition of midpoint.
Yeah. Now, I was tempted to say because of the midpoint theorem that we just encountered. But what we're proving is the midpoint theorem here. So I can't use it as a reason. Okay? I can use the definition of midpoint as a reason. Because we've already proven, or we've been given that definition as to what midpoint means. And we're trying to prove the midpoint theorem. Once we prove it, then anytime we come across a problem in the future that we don't have to reprove it. We can just say the midpoint theorem. Okay?
Okay.
So 3 should be let me think for a second what 3 should be. I'm trying to prove that AM equals 1/2 of AB. And we've proven that AM equals MB. Let's see, let me think for a second. These are so much harder when they don't give you either the statement or the reason. We know that AM equals MB.
AM plus MB equals AB. Which should be like the second additive property or postulate.
What was it again?
AM plus MB equals AB.
AM plus MB
equals AB.
By what reason?
Wait.
And I don't know that that helps us. Well, yeah, it does help us. Okay. That certainly is going to lead us to our final statement. Because if I can write that, then I can take half. In other words, I know that AM plus MB is 2 AM. In other words, statement 4 is going to be 2 AM equals AB based on what?
Substitution?
Substitution property of equality. Now, statement 3, let's just hold that for a second. So that's statement 5, and why?
Because it's the prove-it.
What do I have to do to statement 4 to turn it into that?
Divide, division.
Both sides by 2, correct?
Yes.
Okay. So we're going to use the division property. So the reason for number 5 is going to be the division property of equalities.
Okay, and for number 2, could like AM be congruent to MB? Is that just the same thing?
For number 3, we're still looking for a reason for 3.
Well, for number 2.
Well, for number 2, you've already got a good reason. That's the definition of midpoint.
But like for number 2, like the part. Okay, never mind. I get it.
What we're missing is the reason for number 3. Why is AM plus MB equal to AB?
Because you're just adding them.
Segment. Segment, and this is a postulate. The segment postulate of addition, or the segment addition postulate, perhaps.
Yeah.
But there you go. That does it. In other words, the idea with proofs is kind of what you have to do when they get harder and harder, is you have to work out the logic in your head. It's not, if you can work out the logic in your head, then you can figure out the sequence of statements and the sequence of reasons. But it's very important that you work out the logic in your head. In other words, what we first did was said that equals that. And then based on the segment, that makes statement 3 correct. And then, based on substitution, since MB is the same as AM, I can substitute for MB AM. So statement 4 could be AM plus AM equals AB, which is 2AM equals AB. I might have left out a statement here, which is, it's easy to do, leaving out statements. In other words, you see the statement I maybe should have stuck in between here. Here, I'll write it down here. Let's call this 3.5. Maybe I needed to say this. AM plus AM equals AB based on substitution. And now, number 4 is 2AM equals AB based on addition property. AM plus AM equals 2AM. And finally, based on the division property, we get to line 5. Whether or not I need this line 3.5, probably. Just because that's not just one step going from 3 to 4. That's 2 steps. In other words, I can't just substitute AM for MB and go straight to 2AM. I have to do AM plus AM equals AB first, I believe. I really think this 3.5 is probably needed in there.
Okay.
Do you have answers on these? Do you have answers?
Sorry, what?
Do you have answers on these?
Let me see.
It'd be useful to know if you can look up the answer and see whether we need that line between 3 and 4 or not.
Okay, I found like what we did in class notes. So 1, M is the midpoint of AB, of line AB, and then 2, AM, the line AM is congruent to line MB, or AM equals MB. And for the reason for number 2 is definition of midpoint. And for number 3, it's AN plus MB equals AB.
Okay.
And for the reason, it's segmentation postulate.
Okay.
And for number 4, it's AM plus AM equals AB.
That's my line 3.5. So we do need that.
And then 2AM equals AB, 2MB equals AB. And that's all in number 4. And then that's just substitution.
Okay. So there should be 6 rows, not 5.
Yeah.
So we do need this row right here.
Well, there's like AM plus AM equals AB, MB
Plus, yes, and MB plus MB equals AB also.
and then like UAN.
Yeah, you want to include both of them. In other words, we're trying to prove that, and we're also trying to prove that.
And they're all the same line, though. So.
Yes, I know. I understand that, yeah. Just like our line 5 has both of them on there. Well, line 3 should have both of them on there, and then we should have an MB plus MB equals AB also. So yeah, we left out a little bit of writing here. But the key was we figured out that we need this line 3.5 in there. Definitely need that. And similar logic for MB. MB plus MB has to equal AB also. Okay. So, kind of like the way they put this on the right. Reasons used in proofs. So I guess postulates are also properties from algebra. So we probably could use the word postulate wherever we use the word property.
Okay.
Now here's the second theorem they gave us that we're supposed to prove also. Let's see if we can do this. What's the given?
Ray BX is the bisector of angle ABC.
I'm going to abbreviate just because they don't give us a whole lot of space here. Okay, what are we trying to prove? We're trying to prove that the measurements, and this might be my little thing, I like to write the last line down because that kind of helps me in my mind figure out the kind of logic I need to use. And that's the other half of it, okay? This is similar to the previous problem in that we're going to do both of these each step of the way on the same lines. You with me?
Yes.
Okay. So let's see. We're trying to prove that ABX is equal to half of ABC. Very similar to the previous problem.
Yeah.
So what can I say in line 2?
The measure of ABX equals the measure of XBC.
Mm-hmm. Or is congruent
Yeah.
with XBC. Mm-hmm. And that's because of?
The bisector definition.
Mm-hmm. Okay, and also, I guess that's all that goes on that line. So the next line has to be what? I believe it would be the measurements of angle ABX plus the measurement of angle XBC equals the measurement, or is congruent to the measurement of angle ABC. And that is the segment postulate addition, angle segment addition postulate, maybe?
Angle addition postulate?
Pardon?
Angle addition postulate?
Yeah, okay, yeah, that should suffice. But it's really kind of like two line segments make up a line. Well, these two angles, angle 1 and angle 2, make up this whole angle for the same reason that two line segments make up the whole line. Instead of the addition postulate, or line segment addition postulate, it's the angle, perhaps even the angle segment addition postulate. Maybe if we stick the word segment in there, I believe that would be appropriate.
Okay.
And let's see, on that same row, no, that's all we have to put on that row, I believe. Okay.
It's like last time, so it'd be like the measure of ABX plus the measure of ABX equals measure of ABC.
Exactly. Measure of ABX plus the measure of ABX. All I'm doing is substituting, equals the measure of angle, or is congruent to the measure of angle ABC. And that is substitution again. I really think they should let you get away with making your reasons just say substitution. And also, now here on the same line, we want the measure of XBC plus the measure of XBC is also congruent to the measure of angle ABC. For the same reason, substitution.
Okay.
Erase this because I think we need another line in there. We do. So 5 is 2, right?
Yes. 2 measurement of like ABX equals the measurement of ABC.
It's congruent to the measurement of angle ABC by substitution, and also to measurement of XBC is congruent to the measurement of angle ABC, also by substitution. And finally, there's only one more line needed. That's that line right there. What I'm wondering is if we need to make the jump from congruency to equals. In other words, they want us to prove it's equal, not congruent.
Don't they mean the same thing?
What's that?
Don't they mean the same thing?
Well, maybe, but not always. If I say this angle is equal to that angle, that might be correct because they're positioned the same in space. But if I say this angle is not going to be equal to that angle, but I could say they're congruent because the measurement is the same. In other words, if the measurements are congruent, then the measurements are equal. So we may need an extra line in here to jump from congruency to equality. I don't know, do you have the proof on this one also? Do you have the answers?
Yeah. Let me see what's.
And this last reason, of course, is just division. Let's go through line by line and see what your notes say.
Okay, so for number 1, it's ray BX is the bisector of angle ABC.
Okay, because of
Yes.
given. Okay.
And for number 2, it's measurement of ABX equals the measurement of XBC
So it's not congruent, it's equals?
equals.
Okay. So I don't need any of these congruent signs here. Let me get rid of them.
Yeah.
Okay, I guess once we're talking about measurements, then it's equal. And that makes sense, right?
Yeah.
In other words, if I'm talking about the measurements of these two angles, they are equal. I could say the measurement of that angle is equal to the measurement of that angle. If that angle is 60 degrees and that angle is 60 degrees, then I can say the measurements of the two angles are equal. Or I could say this angle is congruent with that angle, and therefore the measurement of that angle is equal to the measurement of that angle by definition of congruency.
Yes.
So if you did start out with congruency and you have to make the leap to equals, the reason is always definition of congruency.
Okay.
This last, like I said, statement 6 is what I've circled here. It's what we're trying to prove, and it's based on the division property of equalities. Or is it? That last reason might actually notice that if we go back and we look at that table,
It could be multiplication property.
it could be a property of congruence, not a property of equality. In other words, the upper half of this table are the properties of equalities, which all tend to deal with variables. Whereas the properties of congruence deal with line segments, angles. Notice here it says angle D is congruent with angle E. Then angle E is congruent with angle D. And you'd have to make a further step there to say the measurement of D equals the measurement of angle E because definition of congruence.
Yes.
Okay. So on the properties for this one, because we're dealing with angles, we're dealing with congruence.
Okay.
I think. Yeah, it seems to me like if you're dealing with just numbers and variables, it's properties of equality. If you're dealing with line segments and angles, where you really start out with congruency, not equality, and then you make a final leap to equality based on congruency, the definition of congruency.
Okay.
Yeah, let's see what else they want us to look at here. Homework. Okay, let's just kind of talk about these. I think you understand these perfectly.
Yes.
How do I get from line 1 to line 2?
Addition.
And line 3?
Division.
Okay, how do I get from line 1 to line 2?
Multiplication.
How do I get to line 3?
Division.
Okay, over here on number 3, how do I get from line 1 to line 2?
Multiplication.
And line 3?
Subtraction.
Okay, on number 4, how do I get from line 1 to line 2?
Addition.
Okay, and line 3?
Fraction.
Line 4.
Division.
Yeah. Boy, these are a piece of cake after those proofs.
Yeah.
Number 5, how do I go from 1 to 2?
Multiplication.
And then from 2 to 3? Distributive property.
Yeah.
In other words, I'm distributing that 3. This is the first time we've run into the distributive property, I think.
Good.
Today. Okay, but that's what the reason would be. And then line 4?
Addition.
And line 5?
Well, division.
Okay, and then number 6, how do I go from 1 to 2?
Multiplication.
2 to 3?
Distributive property.
From 3 to 4?
Subtraction.
And from 4 to 5?
Addition.
And 5 to 6?
Addition.
Division.
Oh wait, no. Division.
Yeah. Okay, I kind of like these kind of problems also, where they give you some. They don't leave a blank sheet for you to do. Those are the hardest ones of all. But they tell you exactly you're going to have 3 statements and you have 3 reasons. So we know we're not going to miss any. In other words, this distinction between congruency and equality that you sometimes have to make, you might have to put in another line, another row, a statement, whereas we know we're not going to make that mistake on these. So reason 1 is what?
Angle addition property.
Yeah, angle. Here, let me write these in here. That's a rare one, right? Usually it's given.
Yes.
Angle addition property. Is this segment? I think it's the segment property.
Okay.
The angle segment addition property. I don't know if we need the word segment in there, but it was certainly in there when we were talking about 2 line segments are equal to the whole line, whereas this one we're looking at 2 angles are equal to the whole angle. So I think it probably deserves the word segment in there also.
Yeah.
And in line 2, AOC is equal to 1 plus 2. Reason?
Angle addition postulate.
Same thing. Angle segment addition postulate. And maybe that's not really the way they call it, but to me it makes sense that that's, you'd put the word segment in there. And then finally 3.
For like the statement part, would we just like measure of angle 1 plus measure of angle 2 plus measure of angle 3 equals the measurement of AOD?
Yes, that's always good. In other words, the last statement in your proof is always what you're trying to prove.
Oh yeah.
Okay. And what am I doing? Why is that true?
Substitution.
Yeah. Substitution property. In other words, if that's true and that's true, then for that angle there, I can substitute angle 1 plus angle 2, and then I've got AOD is equal to 1 plus 2 plus 3. So that's a pretty easy one. Oh, shoot. I apologize. I didn't mean to go over so long.
That's a
Part of the problem with me using this program is that it covers up my clock on my computer, and I had no idea we were 10 minutes past 6. So I will let you go. Hopefully that's been helpful. Although you seem to have a pretty good feel for it already, but hopefully I've added a little something.
Yeah.
Haven't confused you. But no, you're in pretty good shape here, I think. Getting through these proofs. And then the rest of the geometry is pretty straightforward.
Okay.
More like typical geometry.
Okay.
All right. Janessa, I will talk to you next time.
Okay. Bye. Thank you.
Bye-bye.